So we are starting a little bit early, and I do not really know how long this talk takes because I didn't give it for a while. It's like 3 years ago I did my last talk on the subject. The subject evolved a bit in the meanwhile, so let's try how it goes. Let's first probe the audience. So who practices TDD? Classical TDD cycles, Uncle Bob. It's like, I would say, 30% of the audience. Okay. So who practices TDD with any form of coverage? I take anything, like you measure your test coverage in any form. It's interesting. It's some people raise their hands now who do not do TDD. It's really interesting. Okay, so yeah, and what I'm about to present is an advanced form of coverage which is not a silver bullet. So I have to disappoint you. You can't fix all your dynamic language problems with mutation coverage, but you can take it pretty far. Mutation coverage is a very old concept, but up until recently it didn't get lots of attention by industry, but there's lots of academia research, and I have to disappoint academia in that case. As an implementer of a mutation testing engine, I never used their research. Maybe I weaseled myself through, or it was not relevant for the implementation of a mutation testing engine. So all I'm about to present here is my personal experience with my tool, which is open source, which you can try on your project. And I personally consider is also a form of science because it's a repeatable experiment you can just execute. So let's go. Okay. My slides are different because I was on a really tight schedule, so I had no really time to create lots of cool memes. Sorry, there are no inside here. No pictures, no cats, no frogs. But I've got a really good friend who made graphs for me, so I'm super happy about these. But these are not really. These are graphs. Let's move on. Okay, I have to tell you that everybody does mutation testing right now in a form, because you deploy code each time, each day, each deployment. You mutate the state of your code. And the only problem is that the feedback cycle is super long, because you right now deploy a change to your software, which is a mutation. It's a pretty big mutation. Your PRs have like 200, 300, thousands lines of code. If you update dependencies or Rails, it's like 500,000 lines of code, which transitively get touched, not by yourself, but by the dependencies you pull in. Which means that you all should know what I'm going to tell you, but it's not that obvious. Mutation testing is an easy concept, but it's easy to get confused because the terminology authors have to make up to make mutation testing efficient is a little bit weird. So right now, everybody of you, regardless if you run tests, if you have no tests, production is your test. If you have an issue tracker, that's your test. That's your feedback mechanism on the mutations you deploy. So mutation testing, when I talk about mutation testing, I do not mean mutation testing because we all do it. I mean automated mutation testing, fine-grained mutation testing. Mutation testing that is applied at certain blocking stages of your development. It might be local. You could say, I need to test a specific class before I push it. Or you can have it on CI, which is the ideal case. So everybody sees that you did this work, this exercise, and it's actually reproducible outside of your development environment. So when we move to the next slide, which I should have done earlier, is the automation of mutation testing is key to improve coverage beyond what you can achieve with line coverage and branch coverage and all the other forms of coverage. As I covered the slide already, I will move on already. So first, I tried to write correct software for a really long time. I failed heavily. I failed bigly. It's a really nice adjective developed by some president. And he didn't get the joke. It was a Trump reference. He says bigly all the time. Sorry. Okay. Yeah. So I tried to contribute to certain open source projects. These open source projects were Datamapper 1 and Datamapper 2, which later turned into ROM, and I left the project meanwhile. But what we did there is we ran so-called metric-driven development. So we told to ourselves, human discipline varies over time. Today you have a good day, you spot everything. Your coworkers do a pull request, do a review request, and they are capable to see all the problems in your code, flag them, or you are in the review role and no problem. But there will be other days. These other days are the problem. These other days are the days where you start a long branch, merge a long branch, and your net contribution to the project is actually turning negative. And this is what I experienced in painful iterations over years. And there must be a way to fix this. So this is a graph what happens. It's not a scientific graph, it doesn't even have access, but it describes on how humans are not capable to maintain a high quality threshold on their contribution. And we must seek out tools and strategies and processes that help us. The Git tool we hopefully everybody uses, any form of version control, is a method to achieve a certain reproducibility. So it's a method to schedule patches. It's a method to send patches to someone else so they can be reviewed. The key is here, how do I personally mitigate the shortcomings of the human brain, and how do I verify to myself that I did the maximum possible or the maximum required to ensure that a specific change set is not affected by a bad day. You can decide to add linters, you can decide to perform TDD, and you can also decide, I perform line coverage analysis. I say, I do not check my code in until I achieved 100% line coverage to make sure that this teeny thing I did overlook doesn't pass into production. And yep, the short evolution of coverage I experienced by myself. So I started with Rails. So and Rails has this famous test-to-code ratio. And nobody talks about this for a reason, because it's bullshit. There is no way the amount of lines you write to test something corresponds to the correctness of your test suite. Then there is line coverage. The line coverage is what about like 15 to 20% of the people in the room are right now using. But the line coverage is lying to you also, because it never verifies what's actually tested. It just verifies that the code is executed, which is a big difference. Then there is statement and branch coverage, which is a step up, but there is no tool available for Ruby at all. So, or call me wrong, I would really like to hear the audios later tell me like, there is a branch coverage tool, I would be super happy to see it. But even with branch coverage, it only guarantees that the branches were reached, not that they were executed. So, and there is mutation coverage. So this talk is about mutation coverage, and mutation coverage forms hypotheses, automated hypotheses about your code, about commits you could do, executes these commits against your test suite, and determines, does my test suite detect the change? How can a test suite detect a change? Because the test suite is green right now. Right now, everybody of us should, in canonical TDD-style development, have a CI with a green test suite. The mutation testing theory says, if I do a change and the test suite turns red, we are covering this change. So this change is not good, else we would have written it by ourselves. So, and if I circle back to the beginning where I said everybody of you does mutation testing, assume you would right now on a bad day deploy a bug to production. Well, the first thing you do is you write a test against this bug and check it in. And this is what the mutation testing engine does for you to a limited scale, because it's a stupid engine. It's not a human brain which can understand the semantics of your code. It can just do some small strategic changes of your code, asking the test suite, hey, do you detect this change? So this is not a bug you are about to check in the future. I see still confused faces happens, probably because I didn't explain it enough in the last 3 years, so let's move on. Let's talk about an awesome graph my friend made. I will not point him out here. The orange circle is your application. It's the desired semantic coverage of your application. And the red bricks represent the parts of your application which you are able to cover with tests when you do traditional TDD, and the area covered is the amount of coverage reported by line coverage. And as you see, there is no way with rectangular bricks, with big rectangular bricks, you can verify that your tests cover the entirety of your application. There's no way, the bricks are too big. The bricks correspond to the resolution of line coverage when verifying that your semantics are correctly specified by your application. And my claim is mutation testing can improve, and I will show you, mutation testing can improve this coverage, but it will never be perfect. There's no way mutation testing can replace other forms of verification, but it can replace or shorten other forms of verification cycles significantly, because you do the experiments which you would do on a bad day in production in mass early. You can trigger it early. You can trigger all possible easy, stupid commits against your code base early and get the ones reported which was past your current test suite. Obviously, these commits generated by or these patches generated by the mutation testing engine are never additive. I don't add put as statements. I don't add debug statements. I don't add whole rates controllers. What I typically do in the mutation testing engine, I remove semantics. I delete a line of code. I delete a statement. I invert a conditional. And these are all possible commits you could do in the future. And in case any of these commits is not detected as failing the test, it probably meant that somebody did this commit in the past, and either the semantics in this automatically generated commit are even desirable because redundant code got removed, or they are uncovered and might, in combination with the next deployment, with a pending user hitting this feature, blow up. It might blow noticeably up, or it might just create bad data in your database. Who knows? This is about, a human has to decide how one of these possible commits reported by a mutation testing engine gets handled in your application. And this is an oval. An oval is easy to assume we can just make the brick smaller and smaller and can just create an integral really close. So we are at 99%. At 99% semantic coverage, which is unachievable even with mutation testing. But real apps look like this. The requirements on real apps are weird. You can't put them in mathematical forms. So if you try to approximate the real application with tests, you will always fail. The only thing you can do is reduce the delta, the measurable delta, to a minimum. You can use line coverage to achieve like a first level, but you should go further. And that's my message here. You should consider your test suite incomplete until it passes mutation testing, which sounds outrageous, because how can this person on the stage just tell me, I am at 99% line coverage and I worked so hard for it, and he just tells me I should work even harder, should work 10 times harder, because I, in my own experience, I'm speaking as a potential developer being introduced to mutation testing, I worked exponentially harder to cover the last 2%, the last 1%, to get close to the 100%. It was so hard. Why should I even try to go into the fractions? Because mutation testing tells you which code you can remove. It's a dead code elimination system. If you have a coercion in your code, you take params in Rails, you pop out a key, and you turn it into an integer. Fine, but maybe this specific param was already an integer. Super bad example because they all get submitted as strings. Let's go to another example. You have an API which is supposed to read a certain amount of bytes from a file. You take a parameter and you just call blind 2i on it. Maybe this one is not required. Maybe you don't even need the 2i, but nobody ever did the experiments against your test suite. And this is all mutation testing is about. Mutation testing automatically does all imaginable experiments against your test suite, against your code, measures this with your test suite, and makes sure that it shows you the possible removable code or possible unspecified extra semantics, which might be better be specified. So let's go and show you the shortcomings of line coverage. This is an example method. I will redefine this example method multiple times. And this is an excerpt of an RSpec which just runs this example. This example has 100% line coverage and it verifies nothing, but there is no exception raised. It has zero. It provides zero value to your test suite. It just runs the code. It does not assert its inputs. It does not assert the outputs. There is no expectation. There's an expectation missing. We all have written these kinds of specs. Everybody in this room has checked in a specification, an RSpec or a mini test, where you did lots of setup. You worked really hard to set up your mocks, your database state, whatever. And then you just ran your method and forgot to assert its side effects, its return value, or its overall impact on the system. And line coverage cannot detect that one. Branch coverage cannot detect that one. Mutation testing can. I will later show slides where this happens. Let's talk about another line coverage example. This one is pretty common to me. This happens always. Because we are in a dynamic language, we cannot verify call sites. All call sites are dynamic, which means that I often place rarely used functionality behind a method call. And I do a stupid single typo in the method call. Line coverage, even 100% line coverage, does not protect me against that one, because it doesn't verify that this typo is actually executed. This is where branch coverage, this is what branch coverage would cover this. Branch coverage would tell me, hey, the else body of this if guard, the conditional body of this if guard is not executed. And it would report me that fact. But right now, line coverage, which is the only thing we can use apart from mutation coverage in Ruby, will not help us. Let's go to branch coverage. So, one moment. Mutation. There is, yeah, I mixed up my slides. Sorry, I will go back. This is a branch coverage counterexample. Here we have a specification. We have a specification of the side effect A. And we have a specification of the side effect C. But we do not have a specification of the side effect B. But branch coverage would still report, hey, all branches are hit all the time. We are done, which is not the correct result of a coverage checker. Let's look what Mutant would do. Mutant would report you exactly that. Mutant shows you a diff of a possible commit you could do, and it tells you, the tests I ran against this modified example did not, look at this test. This test would not detect it. Obviously, this is pseudocode. If I would expand it, it would not fit on the slide. But this mutation is a typical report of an AST-based mutation testing engine. It tells you, I can remove this instruction. It's a so-called semantic reduction. I can remove this instruction, and your tests still pass. This is a commit your coworker is about to do tomorrow because he sees no test. This is a commit which triggers a feature which is super important, which is not specified at all, and it might be broken without your knowledge. That's the message of mutation testing. That's the value you get running a mutation testing system against your application. Okay, obviously, as I said, no silver bullets. This one is shit. Because Mutant will just do it. Mutant will just go in and, as it removed the side effect do C, it removes your loop termination. There is nothing you can do as an author of a mutation testing engine. Also, maybe we can solve the halting problem, but if I could do that one, I would not present here. I would do something else. I work for people that would pay lots of money that I do not talk about the fact I solved the halting problem. So, this is the limit of mutation testing. Mutation testing will generate mutations that are equal to the original code, and mutation testing will generate mutations which do not terminate. Thankfully, we can detect the latter case, because while it's theoretically not possible to detect if this code would ever terminate, we have a baseline. The baseline is our specs were green before. If our specs had infinite runtime before, we would have noticed and not checked them in. So Mutant's assumption is, at that case, this case can be solved, just run your test in a timeout. If the timeout triggers, Mutant assumes this mutation is detected. Because if you had done it by yourself, your test suite would run infinite time, and you would not probably at some point gave up and just said, okay, it's a bad change. So, okay. Recap. Let's go to the slide I missed, because that's the, this one should be way more down. Okay, recap. Mutation testing is not a silver bullet. Mutation testing is for code which is business relevant, essential. That's the message here. You cannot rely on dynamic language code where you have no other means of verification. You have no type system. You have no totality checker. You have nothing to guarantee that your tests cover the semantics of your project to a verifiable degree. And this is automatically verifiable. You don't have to hire a consultant. You don't have to hire a high-profiled security team which writes a domain-specific fuzzer to trigger your code. It comes for free. It's just CPU time spent, and our time should probably be worth more than the CPU time spent to run a mutation testing system. Obviously, there are the shortcomings I mentioned already. There is a specific discussion about equivalent mutations, which are cited by academia as the biggest problem in mutation testing. I can only say here, from my personal experience, I run this project for 8 years. I've killed millions of mutations, and I only had 1 or 2 equivalent mutants which needed a workaround. So in real-world code, it does not really happen. It's a really easy example you can give, because the canonical example of an equivalent mutation is a for loop. A for loop where the exit condition can be mutated to some which is equal but has different syntax. And I don't write for loops with indexes in Ruby. I use array.each. And there these mutations cannot occur. So each time you see an equivalent mutant cited by academia when you do follow-up research, which I hope after you see this talk, is ask yourself, would I write this code which is affected by this equivalent mutation And in 99% of the cases, the answer is no, because we use a high-level language. We don't loop over an array with explicit indexes. We use a library function which does this. So here I have to disagree with academia, and I will receive more hate mail after this talk goes online. Okay, so here's the counterexample. When we talk about mutant and mutation testing, I need to make up a new namespace. It's a new domain. Like when you work in e-commerce, you need to learn what a cart is. You need to learn what a checkout is. These are domain-specific terms. So this talk is part of the workshop. So there is a mutation testing workshop, and the idea of this talk is that I prime everyone who wants to attend to the workshop with a nomenclature so we can move on. And in case you cannot attend the workshop or do not want to, you should at least realize that these are the domain-specific terms for mutation testing. I will go through them one by one with a little bit more verbose explanations than the slide can give you. There is a match expression. The match expression is something I made up. Because when you target the mutation testing engine against your app, you do not want to be forced to have a giant config file which lists all the methods, which lists all the classes. So there is a matching system, like an expression like you are used to when you're talking about instance method and singleton method, just made up the star, which means mutate everything inside this namespace. This is a match expression. Whenever you in the future deal with mutant, you will see the term match expression. The match expression allows the mutation testing engine to automatically discover subjects. Then there are the mutation operators. The mutation operators are, I stopped counting at 180. So Mutant has a really wide set of mutation operators. That's not because Mutant is a really good tool. That's because Ruby is a complex language. And everybody who disagrees should look at the AST specification and compare it to a language which has more design cycles like Haskell. Haskell looks complex as concrete syntax, but if you look at the various different AST nodes, it's a much less. Like it's derived from the lambda calculus, which has much less internal primitives. It's all about composition, and Ruby is not about composition. Ruby is a language which adds more primitives to overcome its internal shortcomings, and the fact it's a dynamic language which you cannot easily refactor. But that's something you can poke my head. I could do a whole talk about on how dynamic languages are inherently leading to add-only systems, but that's not a talk here. So that's just an example of an operator. We call that one statement removal, and it would be a relatively pointless exercise to go through hundreds of slides where I explain each one. A current shortcoming of Mutant is that you just see the application of the operator against the subject, but you do not see the name of the operator. We do want to fix that to automatically generate a link to the documentation on the report, but this has to be set like that. Okay, so then there are the subjects. The subjects are selectable things from match expressions. So Mutant currently only can mutate instance methods and singleton methods, or class methods, depending on the team I talk to. This is because I personally believe that all code which is in DSLs is like a constant. It's a constant expression, and I do not test my constants, and I will not go into this decision, but Mutant is limited to singleton methods and instance methods, but the bulk of your code is there. And line coverage can cover that your class body is fully executed, but that's implied, because if the only reason your class body would not be fully executed is when you have a syntax error and it cannot be loaded. So, okay. Then there is the mutation. The mutation is a mutation operator applied against a subject. So like in math, you have the result and the operator. The mutation is the result of applying a mutation operator against a subject. Then there's integration. Mutant currently has one public integration. There are private integrations for companies who wanted me to do special stuff like implement Mutant against their domain-specific DSL to describe certain off-mainstream properties. But the term implementation will come up. So I will ask, like, which implementation do you use? The custom one? Do you use the experimental mini-test one? Or do you use the RSpec one? Then there is a term adjective, mutation. The adjectives are dead or alive. And a live mutant is a mutant which can be reported as a commit you could potentially do in the current test suite state. A dead commit, a dead mutation is a mutation being not reported because your test suite could detect this mutation. So alive mutations are the ones you should deal with, and dead mutations are the ones which are good, so we kill mutants. And there is the isolation, the whole topic of isolation. Mutant reruns your tests one time per mutation, and it tries to be intelligent about the subset of tests. But isolation is super important when you deal with Rails, and there will be a dedicated slide. There will be a dedicated slide when it comes to Rails. Isolation is a property that no effect, the effect of killing a mutation on a subject against your code, against the global state of your code, observable, leaks into the next mutation. Imagine we did one mutation which closes or turns down the connection pool to active record. All future mutations would come back dead because of a spec failure. Okay, assuming your tests touch the database, which is, to be honest, in cases in all, I've never seen a Rails app without a spec who doesn't do this. So we have to deal with isolation. Okay, let's continue. As Mutant has some future challenges, I got some funding from some really, really nice companies who approached me and said, hey, could you continue on these features? There will be an official mini-test integration soon. I got the funding secured, so a company which is not announced yet, it will be announced on in the README or on social media channels soon. Then there is a big challenge of test selection. If your current test suite, so raise your hand if your test suite runs longer than 10 minutes. Okay. Raise your hand if your test suite runs faster than 10 seconds, entire app. Nobody, because this would not be an application, it would be a toy project. So, imagine 100K log Rails application. It generates around 1.5 million mutants. 1.5 million mutants times 10 minutes is, let's say, to at least, it feels like heat death of the universe. It's not the case, but nobody would wait for a result that long. The key is here, mutation testing engines, just like Mutant, need to be able to identify, let's go back to the terminology page. Where is the terminology page? There. Mutation testing engines, like Mutant, need to know there is a subject. This subject is probably covered by a specific test, and I only run this test to kill the mutations in that subject. And this is a really big topic. There are various different approaches. Mutant right now assumes that you all are good RSpec citizens and tag your tests with the method or class you are testing. So when you write describe, my controller, sign up, whatever, Mutant will be intelligent enough to target the mutation killings against subjects emitted from your sign up controller against this test suite. It won't run your login controller's test. With good test selection, mutation testing on a 100K log Rails app can finish within one and a half hours. But you do not run mutation testing against your whole application all the time. You typically limit it to your current working set. It's not on the slides. I should probably have put it on the slides. Mutant has an incremental work mode. It's a so-called since flag. The since flag allows you to specify a range of Git commits Mutant's test selection will be filtered with. So you can say since the last master merge, since my current commit had, and it will automatically apply the match expression I explained above against the filter and only run what you touched in the current iteration, so it can finish within 30 seconds. It's really good parallel CI task, so nothing to worry about. You can throw it on your app right now. I would really like to get Mutant running on JRuby because, in my opinion, it's a superior runtime. But JRuby has no fork, and right now Mutant depends on for isolation properties to avoid poisoned global state leaking into the next mutation. It relies on native POSIX fork. So I can't do this right now. I talked to Charles today again, and there are ways around in JRuby. We can boot several VMs inside one JVM. This is about to be solved. It's still an open topic, but I'm committed to finally solve it. And Mutant doesn't on a single machine doesn't scale well beyond 12 CPUs. So I've tested it on experimental CPUs up to 128 cores, and above 12 it doesn't make sense anymore. This is because the Mutant master process is itself implemented in Ruby, and it simply chokes on the amount of events. So I need to fix that one. And there is distribution. So there are private forks which have distribution. It's not in the public version yet because people like to pay for Mutant features, but they do not like to pay for the amount of extra work which is required to put in open source because it needs to be generic. It does not need to. It shouldn't be hardwired. Okay. So now the promised Rails specific. So I had Rails in my talk title, and this is the only Rails specific slide. I'm super sorry about this, but I predicted that I see lots of confused faces, but I attribute this to my presentation skills, not the subject. With Rails, evaluating match expressions is hard because of the autoloads. Seriously. So you need to set up a special rates environment where all autoloads are automatically expanded, so Mutant can find your subjects unless you do want to maintain a really long config file. With Rails, lots of subjects are dynamically generated. As long as there's no source code, Mutant cannot mutate. So right now I have to skip about dynamically generated methods. There are possible architectures around this, but I couldn't yet convince myself to implement it. And there is the integration with test frameworks, as Rails is particularly nitpicky about typical Rails projects I start to use mutation testing on, have always these weird half-initialized RSpec setup which gets loaded over the course of the execution. So sometimes Mutant doesn't on Rails projects find your tests, and there are ways around it. And in the workshop we go through the commits which are required to make Rails Mutant Rails ready. And there is isolation because most Rails tests touch the database, and when you touch the database, you potentially can read the state from another thread. Mutant is multi-threaded, so all the state can leak. So you need to have a really good database cleaning setup, and the default database cleaner doesn't always work. I will go into that also in the workshop. So that's it, and I would really like to take questions in the 3 minutes remaining. And sorry for speaking that fast.
Ребят, у кого есть вопросы? Не стесняйтесь. Ага, бегу.
If nobody has questions, I assume everybody understood everything and I ask questions, so make sure.
This side.
Okay.
Can you answer in a few words how actually mutations are performed? Do you use some Ruby grammar? I don't know. So how?
Yes. So what I do is I first run the merge expression. The merge expression finds the subject. So for example, it finds the object which represents a method object, and then I wrote a custom version of. I use the source location information to trace back to the source. I parse that file. Then I find the AST node which corresponds to the method definition and run that method definition against the mutation testing engine, piling up all possible mutations. And per mutations, I fork so the effect doesn't leak, and eval a generated file with a mutated AST back into the VM. So to do this, I utilize a really great gem called Parser. And I wrote the unparser gem, which is capable to turn AST back into concrete syntax. And if you want to see the specifics, I'm super happy to show you.
Thanks.
Good question. So thank you. Any other questions? I like questions. I would do the entire talk as a Q&A if I could.
Hello. Thank you for your talk. I have a question. Do you have any ways to visualize the process of displaying failing tests in a mutant?
If I have any ways to visualize the quality of tests?
No. Failed examples. For example, I have a subject that fails, that they didn't cover the case.
Yes.
Yep.
So, okay, so let me just first correctly repass the question so the audience has a chance to. So if I have a concrete example which shows the entire workflow, yes. There is a concrete example in the README. I was super confident you could execute it against Virtus, a gem which is not in vogue that much anymore these days. But there is a concrete example, and the CLI should still work. But I'm basically back from a big OSS communication pause, and I will use the workshop material I created to push much more examples up after this conference ended. So, and you can also find me on Twitter and just ask to be guided through. I like this. I like to doing this a lot. So. Or attend the workshop, which I would really like.
Markus, next question.
Yeah, sure. Next question.
Hi, thank you for the talk.
I have a little bit louder, please. You need to be super loud so the echo doesn't cancel.
Yeah, all right. Thank you for the talk. And I have a question about when you introduce mutations, there could be a lot of combinations. It's just combinatorial explosions. Yeah, and how that's how do you limit them?
So Mutant right now does so-called first-class mutations. So all mutation operators have a match selection. So they walk through the AST and search for certain patterns, and only when the pattern is present, they fire. There are really primitive operators, which are the most powerful ones, which is statement deletion. You saw the one where I removed the do see instruction or method call. And there are very complex mutators which only fire in certain combinations of method calls. So there is the possibility that you mutate the mutated output again, which is called high-level mutations, but Mutant, for operational reasons, intentionally doesn't implement them. And it's in the community also a big topic because some people claim mutation testing is worthless without high-level mutations, and I heavily disagree. And going further into the details, I would like to, but I think it would blow this Q&A up.
Thank you.
Hi.
Hi.
Markus, I'm here, right? Yeah.
Hi.
Hi, thank you for the talk and for the jam. I've used it about 2 years ago in small libraries with 100% of coverage, yeah. But now I have a question. When I use the mutation coverage on small gems, it was quite a big time to...
Yes, it's very likely that due to the fact that on normal development, you do not have to be perfect with your RSpec metadata. And on normal development, there's no reason to fix a typo in your describe statements. But with Mutant there is, because without this information, Mutant cannot target your test selection, and it will execute far too many tests which are totally unrelated. So it's very likely what happened to you. Or you used a version which was not capable of concurrency. So concurrency is a big winner here.
My question is, do you know some examples of applications, not gems, who progress in mutation coverage?
Of applications. So if I know examples of applications which are public, which do full mutation coverage, I have none of such. Because I would expect that only the group of Mutant developers or related contributors right now maintain such applications commercially. There are some libraries out there, some really complex libraries which aim for full mutation coverage. But there is no public example. If I have one, I would happily point to it.
Yeah, thank you.
Друзья, это был последний вопрос, к сожалению. Иначе мы выбиваемся из тайминга. Давайте еще раз скажем спасибо нашему докладчику. Марко, thank you very much.